This video looks at translation of parabolas or translation of quadratics. This is from page 218 in the text. So they start off, you can use translations to find different features of the quadratic function. For example, y equals x minus 3 all squared is a horizontal translation of y equals x squared, moving 3 units to the right. So they're essentially saying you started with y equals x squared, they replaced x with x minus 3, and it moved the graph 3 units to the right. So here is your y equals x squared, and they've moved this 3 units to the left, so your center or axis of symmetry is moved to x equals 3. And y equals, so from here, and y equals x squared plus 2 is a vertical translation, moving 2 units upwards. So they've then moved this one 2 units upwards, and so you can see your vertex is at the point 3, 2, so x value is 3, y value is 2 for our vertex. So it's moved 3 to the right, 2 upwards. So from here, so y equals x minus 3 all squared plus 2 is a translation of y equals x squared, moving 3 units to the right and 2 units upwards. Notice that the equation of the axis of symmetry is x equals 3, and the vertex or turning point is the point 3, 2. You can change the equation of any quadratic function into the form y equals a times x minus h all squared plus k by completing the square. And we'll look at that later. But now we're just going to quickly look at, well, how the translation works and how you know what moves what where. So say we start with the equation y equals x squared, and say we replace y on the left with y minus k, and that equals, we replace x with x minus h. So we've adjusted our y and x by 2 values, k and h, we've subtracted those. Now, our k is our y, our translation that we've done on y, and our h is our translation that we've done on x. Now, if we add k both sides, so we move the k to the right, we end up with y equals x minus h squared plus k. Now in our example before, that was this, y equals x minus 3 all squared plus 2, and we saw that the negative 3 moved it across to the right, and the plus 2 moved it up. So, the interesting thing is there, if you think of the positive direction of the x-axis being to the right and the negative direction being to the left, well, and we look at the sign of our h here, so negative 3, a negative there actually moved our curve to the right. So it moved it the opposite direction to the sign. And then if we think of the positive direction on the y-axis being up, the negative direction being down, well, our sign for that one was positive 2 or plus 2, and it actually moved it up. So it moved it in the same direction on the y-axis as the sign there, but on the x-axis it moved it in the opposite direction to the sign there. Now, if you go back, so writing our equation in this form is pretty standard with y by itself on the left and everything on the right, but if we move that 2 back to the right hand side, we would have back to the left hand side, we'd have y minus 2, let's just move that off the way, y minus 2 equals x minus 3 squared. So that's if we subtracted 2 but from both sides to get the 2 back to the other side. Now, if you put that over that side, and you look at our graph, it's moved up in the y-axis, but we've got y minus 2 there, and it's moved right on the left axis, on the x-axis, and we've got negative 3 there. So it's now on both axes, it's both moved in the opposite direction to the sine. But because this is a convention to move everything over to the right and have y by itself, changes the sign of k, and so it moves on the y-axis, in the same direction as the sign of k, but on the x-axis in the opposite direction as the sign of h. So that is how the translations work and how the different signs affect the actual movement of the graph. We just have, to finish off, we just have this important box on page 218, and it says, for the quadratic function, y equals d times x minus h squared plus k. So this is what we had before. They've just added this d at the beginning of the parentheses. The equation of the axis of symmetry is x equals h. So h is how far we moved it across to the left or right, and the axis of symmetry being the vertical line where the curve is reflected. And the turning point has coordinates hk. So as we saw up here, our turning point had coordinates 3, 2, because we translated the x-axis 3 and translated the y-axis 2. So the turning point has coordinates hk. It is a dilation of y equals x squared from the x-axis by the factor d from y equals x squared, followed by a translation of h to the right and k up, blah blah blah. Okay, so what's that saying? Well, it says, it said the axis of symmetry is h and x equals h, and the turning point has these coordinates h and k. The dilation is the other thing here, this d, the only thing they haven't discussed yet. And essentially the dilation is, well, how squished or stretched the curve is. So as you might stretch it out this way and have a curve more like this, or you might squish it in and have a curve more like this. See, dilation is how open or like wide or narrow or something it is, how sharp the curve is.